However, the whole idea is that we want to kind of build concepts around time series models. So this first 30 minutes is the most important part of the session. Once you understand different types of time series models and then how they are put to use, then remaining part is going to be more or less a smooth ride, mostly theory. So let's see if we can deal with some live data. कोई non-banking stock. So I am on to the financials. Within financials, profit and loss. Okay. So these are the sales numbers for last 5 years. I'm going to manually plot them into my Excel file one by one. Let me call them as year 1, 2, 3, 4, 5. And this is the value of sales. So these are rupees in crores first year, then second year sales, third year sales. This is March 2013. Fourth year. So we have data of 11. It started from 11, 12, 13, 14 and 15. Now, how do you make use of this data? So what if we wanted to know what would be the sales of ITC in year 2016? Now, of course, the data will be available easily, but assuming that the data was not available and we wanted to kind of forecast what would be the sales with an assumption that the only variable that's affecting sales is your past sales, which means an assumption that all the variables that existed in the past are still affecting the sales. Are you following what I'm trying to say? So one way of doing it is, now we can just plot this data onto a simple scatter plot to see if there is some doesn't show half of the chart types. Okay, fine. So we would plot them on a scatter plot here, and see now how does the data look. So we have now very limited data, but we have sales on the y-axis and we have time period on the x-axis. Now this data we could convert into a different type of equation. Okay, so we have an equation here. Observe this. This equation is telling us that sales in a particular year, is that visible at the back? Sales in a particular year is 5416.2x plus 26659 rupees in crores. Right, so what we just did is we built a very basic type of time series model which would be called as a trend model. Okay, so using this equation now we could, and in fact if you'd observe, we have a really large R square which is about 98%, and using this model now we could predict what would be the sales of ITC in year 2016, which is 6 in our equation. So what you need to do is insert 6 into this equation at the place of x. So just do it. How much? 59,146. Okay, so about 59,150 approximately. So this simple trend model is giving us a value which is about 59,150. That is the first type of model. Okay, so you can write down a trend model. In fact, why don't you write the actual data? So it would provide you easy recall. So heading would be annual sales data of ITC. कुछ लोग एग्जाम्पल सुन के खुश हो गए पीछे. So annual sales data of ITC, and then 2011 to 2015, just plot the sales value. Now let me adjust this graph a little bit. Have you written the actual values? Then write down the equation, and this equation you would call it as a trend model, TREND, a trend model. And then you would write the equation. Don't have to mention the R square, just write the equation. And then say forecasted sales of year 6 using the trend model. Forecasted sales of year 6 using the trend model. And then whatever number we forecasted, 59,156. So 59,156. So what we are learning basically from here, that a time series is nothing but a simple linear regression. Agree? The only thing that changes now, what we get on x-axis is the time, and then your slope coefficient would be a function of time. But apart from that, there is no other change. A linear regression and a time series model prima facie look same. Okay. Now observe this. Now we have a very small data point. I mean, ideally you should have at least 70-80 data points to do analysis like this. But can you see that there is some pattern in these errors? So I'm trying to get rid of this ribbon. Do you see some sort of a pattern? Some sort of a pattern in those errors? Do we have a pattern? It appears that we have a serial correlation here, correct? Because maybe this point is perfectly here, but we have a negative error term, and then we have positive, and then again we have a negative error term. So we discussed earlier that most of the trend will have an issue like this. Okay, let me build a different example to prove you. Let me just fix this graph first. So okay, so I'm building a different data set just to prove this point. This is 5, 6, 7. This is here. Now this you need not write, just observe. And let us say your sales. So this is 100, and let me keep it a function of 1.2. And we have year and we have sales data now. Now let's put this onto a graph. See this now. Can I say that this graph is showing some sort of a exponential growth? Correct? Now if you forecast sales for subsequent period, the data will go up even further. Now if you were to build a regression for this, even without really doing it, my guess is that the regression might look somewhat like this. We might have a line which would go in this fashion. Yes or no? And then there would be a lot of errors which would come below the line, and then remaining half of the errors would be above the line, which means it will exhibit what? A positive serial correlation, which we know is the issue with most of the trend models. So if I were to do that here, okay, then this is the line, and again it clearly shows us that we have some issues with the correlation of the errors. Correct? Now what should we do to fix this error? So any data which is growing exponentially, that is definitely not a linear data. Agree? Data which is growing exponentially, that is not a linear data. Why? Because it is the shape of the curve by itself would be like this. So what we do is convert this data into a log value data. This was what we were referring to in the previous session about transformation. So this is log value of sales, and what I am simply doing is taking natural log of each of those values. So we have natural log of each of those values, and now we will make use of year and the logged sales and now build a new regression. Are you following this? So again, let me do this quickly here. So what we want on x-axis this time, we want year, and what we want on y-axis, we want log sales. Do you see any label? Does it say include label anywhere here? So sweet. Okay, one more. Now I'll not have the labels. So in fact it did automatically. Now because of the scale it just looks like flat points. In fact, if I remove that might be faster. So select data, remove. Okay, now look at this. What we have now, on y-axis we have year, on x-axis we have log of those sales values. And does this relationship appear to be more linear than the previous relationship? So now we would build a regression here, and that regression equation would look like this. Okay, so this is your regression equation, and then this type of model would be referred to as a log linear model. Okay, a log linear model. So give heading as, next heading as log linear trend model. Log linear trend model. Okay, and then what you would do is you would write down year, then you would write down log of sales, and then write down the equation. Write down year, and then write down log of sales, and then write down the equation. Now there is an extremely high probability that on the exam you do the kind of calculations that I'm doing now. Now I'm trying to calculate forecasted sales for year 6. Forecasted sales for year 6. And look at how that calculation is to be done. Y is equal to 0.1297 into 6 plus 10.261, and how much is that? 11.04. So that 11.04 is essentially the log normal value of sales, which is 11.04. So then we will say sales is equal to exponential of 11.04, and how much is that? 62,317. So 62,317 is the forecasted value of sales from your log linear trend model. They will never be same. How can we decide which one to use? So if the data is growing exponentially, for example, most of the finance data, you will always make use of log linear models. Okay, and primarily because if you plot the actual sales, the data is never linear, and if the data is never linear, and if you try to plot a linear relationship, you will always end up having serial correlations. So now we still have serial correlation in this data. Okay, but at least compared to the previous version, now we will have lesser issue with serial correlation. Are we okay here? Sorry? Yeah, because the data is very small, the results are inconclusive, Faisal. But had the data points been larger, had we had 70, 80 values to deal with, then we could have seen substantial difference in the relations, especially with the serial correlations. Right? And see, logically, if you look at this, the values are still increasing. Okay, now with ITC data, there is a clear trend in the sales, right? But there might be scenarios where the trend in the sales might not be so easily visible up and down. So with actual data, that correlation effect gets exaggerated. I don't know if you're trying to understand what I'm saying here, but if you have a log data, that distance between the actual logged value and the line, that has reduced substantially. That means your squared errors are now substantially lower. So automatically the quality of regression is going to be better. Are we okay here? Now both of these were trend models. Because the data points are small and the data itself has a trend. Here the ITC sales by itself has a trend, therefore even a trend model was doing a good job. The third type of model now you get an idea and you say that why not model sales of ITC as a function of what was the sales in the previous year, which means sales of 2014 might have some impact on sales of 2015, so on and so forth. Following this? So what we do is, now I'm going to delete this. So we have sales, and then I will say sales at time t minus 1. That means 1 period earlier sales. So this value here is going to be 31993 and this value is 36617, so on and so forth. Is that okay? Now once we have this, then again we can build a regression. Now we have very small data point, but we will see how that regression turns out to be. So to make Excel capture that automatically, this is going to be 31993.06 and let me call this as sales. So your x-axis value this time is going to be sales t minus 1 and your y-axis value is going to be sales, and I have selected labels. Let's hope that it works. X-axis is sales t minus 1 and y-axis sales. I don't know what is that series 2 for. And let me build a equation here. This is the equation. So again, I want you to plot the sales value and sales t minus 1 value. Plot sales value and plot sales t minus 1 value, and then we have this equation. Have you done that? Then your x-axis here is what? Your x-axis value is what? It is sales at time t minus 1, and then your y-axis value is what is the amount of sales we have here. So this should be sales at time t, which means sales of previous year is helping you forecast what should be sales of this year. And then the heading in your notes, you would call this as AR1 model. AR1 model. AR1 is auto-regressive model. So in auto-regressive now, you're using your own sales of last year to forecast the sales of next year. And then how do you forecast how do you forecast sales of year 6? Okay, so below that you can write down forecasted value of year 6. Forecasted value of year 6 using AR1 model, and that would be 0.8998 into sales of year 5, which is 52759 plus 9245.4. How much is that? 5671. Okay, so about 56,700. So your AR1 model is telling you that based on the amount of sales ITC could achieve in year 5, year 6 sales value should be 56,745. Don't think so. Old Wilders method. HOLT. What? I mean, because I have not read about this, I think it is not that method. As in, because I have not read about this in this context. So there are a lot of other names, but the simplest we will call them as auto-regressive, because you would regress your returns based on your old returns. Okay. Now, what if we had to forecast the sales of year 7? Then what we would do is, now we will insert this values here in the equation. Are you following this? And we will insert this value in the equation, and then it will throw us out what would be the revenue of year 7. Make sense? And then this type of forecasting in the syllabus, they have called this as chain rule of forecasting. Now you want to be further more accurate with your model. So what you could also do is, now I'm not going to do it, but just to give you an idea, what you could also do is have sales of time t minus 2, and then that value would be these ones. So the sales of year 3 now would be a function of what was the sales in year 2 and what was the sales in year 1. So sales of 2015 is a function of what was the sales in 2014 and what was the sales in 2013, and then this type of model we will call as AR2 model, and then in this fashion we can build either AR2 or AR3, 4, 5. We can build as many as we want, and later on we will understand that these AR models are built to kind of capture the seasonality of the data. So if you're modeling quarterly data, then the sales of last quarter will have a significant relationship with sales of last quarter of next year. So then in that case you would want to build a AR4 model. Or if you're modeling monthly data, then sales of the same month last year will have an impact on sales of the same month this year. Then you would build a AR12 model, so on and so forth. Are we okay here? So to summarize, time series is nothing but simple regressions. Within time series there are two models or two categories. Either they could be trend models or they could be auto-regressive models. Now trend models, the most difficulty with these, that all of these will have serial correlation, and that is an assumption violation. And going forward in the reading, if you see that if someone says that we have a time series model, then they are always referring to the auto-regressive. Okay, so that's kind of a standard assumption. Even on the exams, if you see a reference to time series, then you would know that the reference is actually to auto-regressive models.